Hey guys, we're going to be doing section 6.2 today on multiplying and dividing radical expressions. Before we get into that, I want to review what we did part of what we did in section 1. And a big part, one of the new things we learned is how to simplify radical expressions. We're going to be taking that a step further today, so I just want us to remember what we did. So let's look at example 8. You should have this worked out already in your notes. Notice we have the cube root of a to the 6th times b to the 9th. Now we first learned this by expanding this out. We wrote it into perfect cubes because we had a cubed root. Perfect cube and a cube root will cancel each other out. So we wrote it in expanded form where we had a cubed times a cubed. Now we did this because if we multiply it, we would go back to a to the 6th. So we just expanded a to the 6th out into perfect cubes. Same idea with b to the 9th. b to the 9th is b cubed times b cubed times another b cubed. Now this is the same thing. See how many we have here? We have two a cubes. This is a squared being cubed. See how we have three b cubes? This is b cubed being cubed. So it's another way of writing this out to where we can cancel it out. Notice that when we take the cube root of a squared cubed, we were left with a squared. When we want to take the cube root of b cubed, we were left with b cubed. Now, the shortcut we learned here, this was all of it in expanded form, different ways of writing it, but the shortcut we saw was that if I have a to the 6th and a cubed root, then it's like taking 6, dividing it by 3, and that's a squared. b to the 9th divided by 3, because a cubed root is the same thing as a 1/3 power. Okay, so 9 divided by 3 is 3. That's a little shortcut that we learned. I'm going to be going back to this today. Okay, we're going to have expressions where they don't work out perfectly like this, and we're going to want to separate it out to where we can use this idea that if I have a cube root, I want to go by powers of 3. Notice these are not powers of 3, but multiples of 3. I want multiples of 3 here so I can easily divide and get this. It'll make more sense as we go. I just wanted to refresh your memory on the different ways that we wrote this out. But today, I'm going to be mainly using that shortcut we talked about where if we have 6 divided by 3, that's what gives us a squared in the end. Okay, so now what I want us to do is I want us to go and let's get to the page that is titled Multiplying and Dividing Radical Expressions. Before we get started in an example, I want to make sure that we understand all the parts of a radical. Okay, this whole piece, this whole expression here is a radical. Okay, now this out here is what's called the index. It's how we know what to call the root. Is it a square root, a cube root, a fourth root? It's based off this number here. So we have a cube root in this case. Now this radical symbol, okay, that's how we know it's a radical. We have a radical symbol. And then the number inside is known as the radicand. Now, the important thing about this is really this index. Because radicals can only be combined by multiplication and division if the indexes are the same. These indexes have to be the same to be able to multiply two radicals. So let's go ahead and jump right in. Example 1. Cube root of 6 times the square root of 2. Remember, square root is where we don't see an index written at all. It's understood 2. These indexes are not the same, so we cannot multiply these two radicals together. Therefore, no. Can you simplify the product of the radical expression? No. The indexes are different. So we cannot go any further with those two expressions. Now we have example 2. Example 2 has the cube root of -4 times the cube root of 2. The indexes are the same, so we can multiply. We multiply the two radicands. So -4 times 2, that is going to be the cube root of -8. So I want to think about, what do I cube to get to negative 8. What number do I multiply by itself 3 times that will give me a negative 8? There's only one option there, and that answer is negative 2. Because I know that if I take negative 2 and I cube it, that would give me negative 8. A cube and a cube root cancel, giving me just negative 2. Now I want you to take a couple minutes and try the on your own 1 and on your own 2. At this point, I want you to pause the video so you can work those problems out, but I'm going to go ahead and keep moving. Pause those so you have a chance to work them, and then you can see these answers. But in the on your own 1, we want to check and see if the indexes are the same. Since they are, we can go ahead and continue and multiply. So what we get here is 9 times negative 24. So that is negative 216. So we want to take the cube root of negative 216. This is 216 is a perfect cube, so that means there is a number that we multiply by itself 3 times to get that negative 216, and that answer is negative 6. So yes, we can simplify this, and we can simplify it all the way down to negative 6. Now looking at the on your own 2, what I should have said before is we really want to stay in the real number system right now. We're not going to go into the imaginary numbers in this part. And so whenever we have the square root of 5 and the square root of negative 5, we can multiply them. We get the square root of negative 25. If I'm wanting to stay in the real number system, then we are not going to go any further. There would be no real root. Okay, if we were to be in the complex number system, then we would have gone further. We would have said this was 5i. So you can either say no real root or that it is equal to 5i. Alright, before we move on, we're going to start getting into simplifying some radical expressions where it doesn't work out perfectly, where they're not perfect square roots or they're not perfect cubes. Before we do that, though, we really need to have an idea of what our perfect squares and perfect cubes are. Now, I know we are good with our perfect squares. We're good with some of our perfect cubes, but if we have those there written on the side, it'll be a whole lot easier moving forward. So let's go ahead and fill these in together. So our perfect squares 1 to 10 are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Our perfect cubes 1 to 10 are 1, 8, 27, 64, 125, 216, we used that just a second ago, 343, 512, 729, and 1,000. Now keep these in the back of your head because we are going to need them moving forward. For example, with example 3. Now this is a process we've done before, having to simplify the square root of 52. What is the largest perfect square that goes into 52? We're thinking about perfect squares because it is a square root. So the largest perfect square that goes into 52 is 4. So that's 4 times 13. So the square root of 4 is 2. And we leave the square root of 13 alone. Now keeping this in mind, we're going to do a very similar process when we get to 1, like example 4, where we have expressions. We want to find the largest perfect square that goes into each. So for 200, let's go ahead and write that out. What is the largest perfect square that goes into 200? That is going to be 100 times 2. Now is x squared a perfect square? It is. Because 2 is a multiple of 2. We're thinking about multiples of 2 because we have a square root. Square roots meaning there would be an understood 2 here. So x squared can just stay there. That is already a perfect square. Now y to the 7th. 7 is not a multiple of 2. So it doesn't work out perfectly. What we want to think about is what would the largest multiple of 2 be that is less than 7? Should be 6. So what we're going to do is we're going to write y to the 6th. Now how many y's are left? Just 1. If just one y is left, we're just going to write y, just leave it to the first power. And we're going to use that process that we thought about whenever we first started the video. Okay, the square root of 100 is 10. We're going to leave the 2 inside the radical because that's not a perfect square. The square root of x squared is just x because we think of 2 divided by 2 is just 1. Y to the 6th, we have a perfect square. Think of it as like 6 divided by 2. So that is y cubed. And then y is left because y is not a perfect square. We cannot take it out. And there is our final answer. We've taken out our perfect squares and we're leaving what is not a perfect square in that radical. So take a second, pause this video, try it on your own 3, and I'm going to go ahead and continue with its solution. We want to try to find all of the perfect squares that go into 108, a to the 6th, and b to the 5th. We want to simplify this. So starting off with 108, we should have found that the largest perfect square that goes into 108 is 36, and that's times 3. 6 is a multiple of 2. We're thinking multiples of 2 because it was a square root. So we leave it a to the 6th. We know we'll be able to take the square root of that. Now with b to the 5th, 5 is not a multiple of 2. So we want to think of the largest multiple of 2 that is less than 5. That is going to be b to the 4th. How many b's were left? 1. Now think about this. B to the 4th times b is b to the 5th. So all we've done is rewritten this. We've expanded it out. Okay, from here we take the square root of each piece. The square root of 36 is 6. We want to leave the 3 in the radical. The square root of a to the 6th. Think of that as 6 divided by 2. So that's a cubed. B to the 4th, the square root of that is going to be b squared. 4 divided by this understood 2. And then b has to be left inside the radical. So our answer is 6a cubed b squared times the square root of 3b. Okay? Now we're going to go on to cube roots. It is the same process, except now we're thinking about perfect cubes and multiples of 3 with the variables, with the exponents of the variables. Let's start with the cube root of 24. What is the largest perfect cube that goes into 24? Looking at our perfect cubes, the largest one is 8. Should be 8 times 3. So we've got the cube root of 8 times 3. Remember, this is like saying the cube root of 8 times the cube root of 3. We can take those apart. The cube root of 8 we know is 2, and we leave that cubed root of 3. This process here is the same idea of what we do with any of these others. We just weren't splitting up the radical. We were taking the square root of each individual piece there. Here I just showed you that we were splitting it up. We're taking the cube root of 8 and the cube root of 3. We just have to leave that one alone because it's not a perfect cube. So now let's go to example 6. Example 6 has the cube root of 54, x to the 5th. So with 54, I need to think of the largest perfect cube that goes into 54. We should be able to figure out that that largest perfect cube is going to be 27. So that's 27 times 2. Now for x to the 5th, I'm not thinking about multiples of 2. I am thinking about multiples of 3 because my index is 3. I want to be able to divide the number by 3 and get whatever that cube root is going to be. So the largest multiple of 3 that is less than 5 is just 3. So we have x cubed. How many x's were left? 2. So now x cubed times x squared is x to the 5th. We have not changed the value of this at all. We have simply split it up into 2 different x's, x cubed and x squared, because I can take the cube root of x cubed. Now we want to take the cube root of 27. The cube root of 27 is 3. because 3 cubed was 27, so we're going backwards there. Okay, now we leave 2 inside that radical. The cubed root of 2, so that's not a perfect cube. The cubed root of x cubed is x. And then the cube root of x squared, that is not a perfect cube, so we need to leave that there so that we can see this answer a little better. I'm going to move that a little closer. Our final answer here is 3x times the cube root of 2x squared. That is as simplified as this value, as this radical can be. So now, pause the video again. Take a second and try to work this on your own, number 4. I'm going to go ahead and move on to the solution. So with this one, we're wanting to find the largest perfect cube that goes into 128. We should find that that is 64. So we have the cube root of 64 times 2. Now with our variable, what is the largest multiple of 3 that is less than 7? Remember, we're thinking like 3, 6, 9, 12. Those are our multiples of 3. Okay, the largest multiple of 3 less than 7 is 6. So I have x to the 6th. How many x's would be left? Just 1. So x to the 6th times x would give me x to the 7th. So we've done this correctly. We've split this up correctly. So now let's take the cube root of everything that we can. The cube root of 64 is 4. And then we need to leave the cube root of 2 as it is. It's not a perfect cube. Now the cube root of x to the 6th, using our little shortcut, thinking of a cube root as like a 1/3 power. That's what it's the same thing as. That's why we're able to take 6 divided by 3. That is 2, so that is x squared. The cube root of x to the 6th is just x squared. And then we're left with x inside the cubed root. So 4x squared times the cube root of 2x is our final answer. Okay, now we are going to combine the two things we've learned today of when we can multiply radicals and then simplifying radicals to be able to go on to simplifying a product and expressing it in simplest form. So we're going to go down here to example 7. We do not want to simplify it yet. We want to multiply first. We want to get it into one radical together and then simplify it as far as possible. We have a square root times a square root, so it can be multiplied. So what we get here, 72 times 10 is going to be 720. X cubed times x, be x to the 4th. So remember, whenever we multiply variables, we add their exponents. Then y squared times y cubed. So we have y to the 5th. Now we're at a place where we were like in example 4 in the On Your Own 3. We need to simplify this. What is the largest perfect square that goes into 720? We're actually going to have to go beyond our perfect square of 10 because the largest perfect square that goes into 720 is actually going to be 144. So that is going to be 144 times 5. Now, since it's a square root, we're thinking of multiples of 2 here. X to the 4th, 4 is a multiple of 2, so we can leave it as it is. For y to the 5th, we want to think of the largest multiple of 2 less than 5. So that's y to the 4th, and we have 1 y left. So now we take the square root of these values. The square root of 144 is 12. We have to leave 5 inside the radical. The square root of x to the 4th. Think of it as like 4 divided by 2, so that is x squared. The square root of y to the 4th is y squared, and then we have a y left. So we have now multiplied two radicals, and then simplified them as far as possible. So we now have it in simplest form. So pause the video again. Try on your own 5. I'm going to go ahead and move on to the solution. Since we have the square root times another square root, we can multiply these. So we need to take our numbers and variables and multiply those together. So we have 45 times 35. That is 1,575. X to the 5th times x is x to the 6th. Y cubed times y to the 4th is going to be y to the 7th. Now we need to simplify this. Again, we're going beyond those perfect squares to 10. The largest perfect square that goes into 1,575 is actually going to be 225. So that is 225 times 7. And now for our variables, we're still thinking of multiples of 2 since we have a square root. 6 is a multiple of 2. So remember we think about 2, 4, 6, 8, 10, so on. Those are multiples of 2 that we would want and that we could easily take the square root of. So I can keep x to the 6th as it is. The largest multiple of 2, less than 7, is going to be y to the 6th. We have 1y left. Remember, this is because y to the 6th times y is y to the 7th. Those are equal to each other. Now let's take these perfect square roots. The square root of 225 is 15. And we leave the square root of 7 alone. Leave that in the radical. The square root of x to the 6th, 6 divided by 2, so that is x cubed. The square root of y to the 6th is going to be y cubed. And then we have to leave the y alone. So multiplying these two radicals and then simplifying their product gives us 15x cubed, y cubed, times the square root of 7y. Now I have one more thing I want us to go ahead and cover today, and it is dividing radical expressions and expressing them in simplest form. We're going to do the first part of division. We will work on the next part during another lesson. So let's look at example 8. Remember the rule for multiplying and dividing. The indexes have to be the same. So when we have this split up like this, we have the square root of 18x to the 5th divided by the square root of 2x cubed. We want to try to combine this and simplify it if we can. Since they're both square roots, we can go ahead and write this as one square root together. So this is like saying the square root, one large one, of 18x to the 5th divided by 2x cubed. Now we need to remember the rules of dividing variables with exponents. So 18 divided by 2, that means we have the square root of 9. X to the 5th divided by x cubed. That means we subtract their exponents. So when we multiply variables with exponents, or variables, we add their exponents. When we divide, we subtract their exponents. So we have x to the 5th divided by x cubed. That is x squared, because it's 5 minus 3. So x squared. We have the square root of 9x squared. We have a perfect square here, and we even have a perfect square here. So the square root of 9 is 3. The square root of x squared is x. Our answer is 3x. So take a second, try on your own 6. Notice that this one is two perfect cubes. So we're not thinking about perfect squares, we are thinking about perfect cubes. Pause the video, take a second to try and work this out. I'm going to go ahead and move on to the solution. Since they do both have the same index, we can write this as one radical together. So we have 162 y to the 5th divided by 3y squared. which means we have the cube root. 162 divided by 3 is actually 54. And then we have y cubed, because y to the 5th divided by y squared, subtract those two exponents, gives us y cubed. Now we want to try to simplify this. Okay, 54 is not a perfect cube, so we want to think of the largest perfect cube that goes into 54. We saw that in example 6. So that is 27 times 2. So we have the cube root of 27 times 2. Now y cubed, we're wanting multiples of 3. 3 is a multiple of 3, so we can leave that as it is. That is a perfect cube. And now we want to take the cube root of each part. So the cube root of 27 is 3. And we leave the cube root of 2 as it is. The cube root of y cubed is just y. 3 divided by 3 would be 1. So 3y cube root of 2 is this fraction is this division of two radicals in simplest form. Okay, so we've covered a lot of this. We have one more piece of dividing radicals. Like I said, we'll see that in another video. But now you have some practice. Let's see how we do with that.